Hi. Very recently, I had a live stream over on my other channel, Mr. Sensible Live, make sure you're subscribed, where I spent some time talking to Flatzoid. Now, I thought that the subject of Geronism and horizons and sextants may come up, so I was prepared for it. Watch in amazement as I take Flatzoid through the basic principles of celestial navigation with a sextant and see him totally misunderstand how it works. Make sure you've got facepalm protection ready. Enjoy.
Support. And then Retro Bull, he says, Gerund went glurf, so it's only fair Mr. S goes flurf.
Sorry, say that again.
Gerund went glurf, so it's only fair Mr. S goes flurf.
Gerund. I said I wanted to speak to you about a couple of things. We started off with Dell. Gerund is indeed the other one I want to talk to you about, because there's been a bit of a conflab between the two of you, hasn't there? So what's your argument about with Gerund? With my mate Gerund? Tell me, what's he done? He's not my mate.
Gerund, the guy fighting for geometric horizons.
Right, tell us what the issue is. What's he said?
I can show my latest video quickly if you want to. That explains it quite easy.
Why don't you drop me a link? I'll happily pop the link into the chat. But just
okay. But let me just explain it to you. Anyway. Please. The argument he gives is exactly what you guys globers give. The geometric horizon is physical. Okay.
Right.
So he's claiming horizons aren't optical. That's globe-based, correct?
No, there is. You're taking one thing and also turning it into another. You have a physical horizon. What you see is the optical horizon. It could be a bit further or even a bit closer than the geometric horizon. Hello? Oh. Hello? You dropped out there for some reason. You back?
I pressed the wrong button by
accident. That's okay. Sorry, I was just... Yeah, I did hear your question. I did reply, but you might not have heard it. I said, you're taking one thing and sort of applying it in a different way. You've got the geometric horizon. If you have a ball, then looking at that ball, there is a physical horizon. Okay, a point beyond which, a straight line from your eye to the top of the ball. But what we actually see, because we're looking at that through several miles of atmosphere, and you have refraction, you see something slightly different. The optical horizon. It may be a bit further, or not quite as far as the geometric horizon. Usually a little bit further.
Yeah, but that's what I'm saying. He's fighting for the globe with the geometric horizon, so that makes him not a flat earther, correct?
So, well, what's
that's just one of the things.
I've not heard. Yeah, but I've not heard what he said. So, what has he said? He said there's a geometric horizon. What about it?
And he says you can't debunk it. And he says science doesn't prove things. And you know what his argument is for why science doesn't prove things?
What's his argument for why science doesn't prove things?
Rocks cause waterfalls.
Oh, do you know, I did see some comment about that in some of your video, and I didn't look into it. I have no idea what that's about. But the thing with the horizon, I'm presuming that the whole thing with that is because of sextants. Is that why?
Sextants, yeah.
Yeah.
He doesn't know how sextant works. Remember when he went on McToons and he said, yeah, you can use the curved adjacent to get an angular reading?
Right. Now,
throwing away what an angle is.
No. I tell you what, just in the broadest layman's terms, what is an angle, Zoid?
Two straight lines meeting at a vertex.
Yep, spot on. I'd agree with that. There's different ways of saying it, but I agree with that. Yeah. So why is there a problem? We have a sextant here, and it's measuring an angle, in this case, between the sun and the horizon, yes?
Yeah, and the horizon, exactly. So he's physically pointing at the horizon, correct?
He is pointing, so the light rays from the horizon pass through the horizon mirror at B and through the scope to his eye, and at the same time we've got the light from the sun coming off the index mirror, bouncing off the horizon mirror through the scope, and he moves the arm backwards and forwards until he gets them to align properly and takes his reading. That gives you an angle. That gives you an angle, doesn't it?
So he points the sextant at the horizon.
Yep.
He seeks where the sun is, and he brings it down to
Yep.
the horizon.
Yep.
And then he swings it left to right to make sure it's all
as low as
parallel with each
possible.
other.
Yes. Yeah. Okay.
So
So we got an
succession.
angle, haven't we? So we got an angle.
Angles angles in succession to the horizon.
in succession.
Yeah, that's what the principle, the sextant principle is based on angles of succession. In other words, A and B have to be parallel to one another to give an angular reading.
Well, yeah, because light reflects with the same. Is it the same instance angle? So if it hits that mirror at 45 degrees, it will bounce off at 45 degrees, doesn't it? That's how a mirror works. If you're stood dead in front of the mirror, the light reflects 180 degrees back to you, doesn't it? If you stood looking at an angle at 45 degrees to a mirror, you'll see off at 45 degrees, won't you? So yes, you're right. You need to adjust that mirror so that the path of light from the sun bounces off A, bounces off B, so it goes directly down the scope, doesn't it? Because you made the adjustments. Yeah. Okay. So that's fine. So what we end up with is an angle between the view he gets through the scope of the horizon and the view up to the sun. That's his angle. That's his angle. Yeah.
Yeah.
So why is that a problem?
You just explained it can only work flat Earth.
No, I haven't.
That horizon, would you agree he's physically pointing at the horizon, correct?
He is pointing at the horizon, yes. Is he at the same level as the horizon?
Straight.
Hold on.
Yes.
Is he at the same level as the horizon? In this diagram he is, but he could be stood on the top of a mountain. In which case,
that's why you have height of eye correction, so you can be more accurate.
Exactly. So if he was that, as in this diagram, an absolute straight line from his eye through the scope through the mirror to the horizon, then that's simple. That gives you the elevation angle straight off. If he's at the top of a mountain, you have to allow for that height, don't you? Because that's extra. That would make the angle too big, because you'd be looking slightly down to the horizon, up to the sun, so your angle's too big. So you correct it back, don't you? You adjust for the height.
Okay, I'm gonna ask you a question. No matter your elevation, altitude, are you looking straight out to the horizon when using a sextant, because it has to stand parallel?
No, it doesn't have to stay parallel. You could use a sextant.
You don't point the sextant downwards.
Well, if
you point it straight ahead of you. That's the point.
Hold on. You point the sextant at. Well, you're pointing at two
90
things.
90 degrees.
No.
90 degrees.
Hold on. Let me answer. You point the sextant at the two things that you want to measure the angle between. They could be horizontal. There's no reason it's not horizontal. If, as I was saying, in this case, we're using it in the standard way, holding the sextant vertically, looking straight through it, you're looking at the horizon. Okay, if your eye, you're sat there in the water, so that your eye level is through the surface of the water, basically, then you don't make a height adjustment, do you? If you're at the top of a mountain, by definition, you're high. You're looking down towards the horizon. That horizon has gone a bit further, but you're looking down to the horizon. You adjust for the height. You even said you adjust for the height.
When you go onto a mountain and you look out, do you look down to the horizon, or does the horizon rise relative to eye level?
It doesn't. That you can see further. Yes. So
the horizon looks higher. The horizon looks higher.
It looks higher,
when you go up the
but
mountain.
it's still downwards. Why do you make a height correction? Why do you make a height correction then?
Because the sextant, to be more accurate, requires the sextant to be on the same plane as the horizon.
No, it has to be horizontal.
Exactly, same plane.
No, horizontal.
As the horizon.
No, horizontal doesn't mean that. If I could be stood at the beach, okay, looking horizontally forward, and the horizon is, to all intents and purposes, horizontal to me. If I'm in an aeroplane and I look straight forward, I'm not looking at that same horizon. I have another horizontal. It's just it's parallel, isn't it? It's another horizontal. Yes. What does horizontal mean? If I hold a spirit level, do I have to hold it down on the sea level? Or could I climb to the top? No, I could climb to the top of the building and I've got a new horizontal. It's parallel to the ground level one.
Sorry, I have to laugh about this. You do know you're literally fighting for flat Earth here. I don't even have
No,
to do
no, no,
anything.
no. No, what I'm saying is, because you're saying you have to, um, you can't take a reading unless the Earth is flat. I'm saying, let's just say, for the sake of argument, that the Earth was flat. Okay, if I go to the building and I use a sextant, I'm not at the same level. I've taken a new horizontal parallel to that lower horizontal.
So it's parallel to horizontal then.
It's another horizontal. Every horizontal stood at this point is going to be is going to be parallel, isn't it? But the point I'm making is, if you don't even need to see the horizon, you don't need to, all you need is a horizontal, don't you? Or a
Yeah,
vertical.
you can create an artificial horizon because of the sextant principle. Like I said,
You mean one of
if you
these?
don't have that, if you don't have that horizontal baseline,
I don't
it's
need a
not going to
horizontal.
work.
This is an artificial horizon. It's
Which gives
basically.
you a horizontal reference.
Hold on, no, it doesn't. That's not how you do
Yes, it
it.
does.
Right, there's an I'll show you then. Shall I? Can I
Yeah,
show
go
you?
ahead.
Okay, so there's, for anyone who hasn't seen one, there's an artificial horizon. You put a liquid in it, and then you've got a couple of filters because the reflection can be very bright, basically. There's one in use. So you're looking down, and you can see the filters make. I think he's looking at the sun by the looks of it. It could be a spotlight though. Dim it
He's
so you
using
can
sun,
actually
yeah.
see it. Yeah. Okay. This is a guy using an artificial horizon. In this case, a plate with some molasses on. There is a horizontal through the molasses. We have two beams of light coming. Listen, I presume it's the sun. So we got a beam of light that's hitting the molasses and a beam of light that's coming down straight to the sextant, which is the normal way you would see the sun in the sextant. So he has not got a horizon to look at, not a real horizon. So what he actually does, instead of bringing the sun down to the horizon, he brings the sun down to the reflection in the molasses. Now that means we've already established that the angle of incidence where the ray of light hits the molasses is the same angle it bounces up. Okay, so where we reach the sextant, you've got the same angle from the sun, the same angle there is twice. So basically, you take the reading, you bring the sun down, so it's reflected. It matches the reflection in the molasses, and then half that angle, and that's your angle of elevation. No horizontal whatsoever, no horizon even seen. You do not
Sorry.
need a horizon.
You just literally said, look at that horizon baseline for the artificial horizon.
No, what you aren't right. His sextant, one mirror is pointing up at the sun. Yes, the direct view. The other mirror, or looking through the other mirror, is not through a horizon. It's looking down, literally, to the artificial horizon.
And he's making them parallel to a horizontal.
No, what he's doing is he takes the measurement. What's the angle? Just as with our first example, this one, just as you're taking an angle between the sun and the horizon, in this one, he's taking an angle between the sun and not looking horizontal out from his sextant, but he's looking downwards to the reflection. But that gives you twice the angle. So in effect, that there's a fictitious horizontal where those two lines meet. So where your direct view comes just to the left of the 2 times HS, because he's got double the angle. So whereas, let's say in this one you read it and you get the height of the sun as 25 degrees, in this one he's looking at the same sun, the same time of day, he gets height of 50 degrees, but then he halves it, gives him 25 degrees. Boom.
Yeah,
No horizon
exactly.
used.
Because he set a horizontal. That's why he made
What horizontal
an
is he?
artificial horizon. The molasses is a horizontal.
It's lower than him, Flatsoid.
So?
He's had to adjust for height, hasn't he? He's adjusted by halving the angle. If I
Exactly, to get to the horizontal.
hello, can you English? Look, so in this case, he's had. in effect, he's taken a reading that's twice the size, so he deducts half the reading. Yes. In this case, the horizon is slightly down, so you deduct because of your height, and it also I was going to say Coriolis. I don't mean that. I mean refraction. It's the same thing, but you don't need to have a flat surface. Where is his flat surface there?
He's standing on a flat surface, the ground.
What does it matter? Okay.
The molasses is on a box, which is flat. It's showing a horizontal baseline for that molasses. That molasses is literally standing level.
Yes, but it's not a flat Earth between here and the GP of the sun, is it? It's a little dish with a flat surface that he's just using as a mirror.
Remember when I told you how a sextant principle works? Angles in succession. You're literally showing angles in succession here. Why do you think he needs to halve it?
He's halving it because he is making a correction for the fact that his artificial horizon is way below the horizontal.
Yeah, so exactly.
Yes.
So
I don't know why you're laughing.
Angles in succession.
Because in this case, you adjust for the fact, so you don't halve this one, but just for the sake of argument, let's say measures that sun as 25 degrees above the horizon. Oh, but the horizon is 1 degree down, so that's actually 24 degrees elevation. That they use the horizon because it's pretty damn close to horizontal from your eye line, pretty damn close. But you have to make corrections. This is nowhere near close, but it's a very simple correction. You just half it.
Because the
How about that then?
Succession.
How about that then?
There we go.
A bubble sextant. No horizon used at all. You establish a vertical.
Sorry, what does a bubble do? It's a level, correct?
A bubble, in fact, is okay. To be level, what does it have to be? You can say it has to be flat and level.
Would it be showing that you can make it horizontal, correct?
What
the
you've
vertical
got,
and the horizontal is perpendicular.
Do
That's
you know
what the bubble level is doing?
I'm not being rude because I mean I don't know whether you would know and don't know whether you would be expected to know. But do you know what is inside that bit where it says the bubble chamber? Where I'm sort of wiggling my mouse.
Guessing liquid and a bubble.
There is liquid in a bubble, but basically you've got a slightly curved top to the container that liquid is in with crosshairs. So obviously, if you're tilted one way or another, the bubble won't align with the crosshairs. So in this case,
it's the same kind of that you have on a theodolite. So you can
I'll bow to your superior intellect on that one because I don't know about theodolites. So anyway, there is actually a light source in there, so that you can see the bubble. The image of the bubble reflects off a mirror back up to the beam splitter and through the scope to your eye. The sunlight, much as in the ordinary sextant, reflects off the index mirror, off the horizon mirror, and you're not even looking at the horizon, and then straight through the telescope. So instead of establishing a horizontal and an angle above it, you're establishing a vertical and an angle from it. So you do not have to see a physical horizon. You're not using an artificial horizon, and it doesn't matter a damn if there's a mountain in front of you or a valley or whether the Earth is flat or curved. It would make no odds. You don't need it. The shape of the Earth you're standing on is not going to affect that reading.
So when you use the bubble level and you're making it perpendicular to vertical, that would mean
you're making it vertical. You're making it vertical.
Yes. So when you look through the scope is perpendicular to that vertical, correct?
Yes. You're basically
horizontal then.
So you've established your vertical by making sure the bubble is properly aligned, which means the sextant is being held. The bottom yellow line that goes left to right, that path of light is horizontal. You did not need to look at horizon to establish that. You did not need to bounce it off molasses. You have established that as a horizontal from the vertical, i.e. perpendicular to it, 90 degrees from it. So tell me why then? So if that red line coming down, that's your 90 degrees vertical, isn't it? That's to your zenith. obviously. The ray of light coming from the sun, you're measuring the angle between those two. So where they meet, so you've got red down and the yellow coming across, and let's say, just for sake of argument, that's 50 degrees off of that vertical. You haven't had to. You haven't. It doesn't matter what you stood on. You know that.
Yeah, it doesn't matter what you stand on because your reference is horizontal.
It doesn't matter. Yeah, it doesn't. Yeah, yes, it doesn't matter what you stand on. So why the hell do flat earthers then, Zoid, say you got to have a flat Earth because you can't get an angle from a curved adjacent? I'm not using the surface of the Earth at all.
Okay.
I'm not using the horizon. I'm not using the sea. Nothing. I'm just using a bubble. Sorry, I'm getting overexcited there. Go on, carry on.
When you take the star's GP,
Yep.
it's on the same elevation plane, correct?
What do you mean?
So when you take a measurement to the star's GP, you need
No,
to...
I don't take a
do
measurement
your
to the
height
star.
eye correction.
No, okay. I don't take a measurement to the star's GP. I'm using a sextant to find out the angle between that ray of light and vertical. With a bubble sextant, I've got a vertical. With an ordinary sextant, I've got a horizontal, so I can deduct the angle from 90 to give me the angle between vertical and the star. So let's say that's coming in 30 degrees above horizontal. Therefore, that star is 60 degrees off of my zenith. That's all I know. 60 degrees off my zenith.
Great. So when you measure 60 degrees off of zenith, you've taken your 90, you've minus the 60 degrees.
No, minus the 30 to give me the 60.
Okay.
Yeah.
So that you're saying co-altitude angle.
Yes.
So you've used your co-altitude angle now to get the distance from the GP of the star to
wherever that star is. I don't know off the top of my head. I need to look it up in the almanac.
Great. Okay, so let's say you've worked it out now and it's 3,600 nautical miles or whatever.
Yep.
That GP from that star has to be on the same line of reference, horizontal, to where the observer is.
Why?
For the 90 degrees to work out, because you're creating a triangle.
No, I'm not. No, I'm not. You've already, right at the beginning, we agreed on what an angle is. It's two rays with meeting at a vertex.
Mm-hmm. That 90 you are starting off with, that's the GP of the star's 90, correct?
No. What I'm doing... well, actually... No, I have my zenith. It's whatever is directly above me.
You standing 90 as well, yeah?
Well, I'm stood up.
At 90 degrees.
Yes, to the 90 degrees to the floor. Aren't I?
Right, and the GP of the star is also 90 degrees to the floor in its position.
But why does that have to be the same? Let me just try. I don't know. I thought about this earlier, Zoid. Okay, right. If I'm looking at you, okay, you're the star, and I'm laying on my back, and you're absolutely overhead. You're at my zenith, yeah.
Mm-hmm.
Okay. I then turn, let's say, 45 degrees. Oh, you're not at my zenith anymore, but you're still here, aren't you? So if
I'm still at your zenith. Yeah, I'm still at your zenith because I'm ahead of you. You're just looking another direction.
I'm looking at another direction. Yeah, my zenith, because I'm round a curve, is different now because I have moved around. I now measure the angle and I find it's 45 degrees to where flat soil is directly above to where I am. Therefore, I now know that I am 1/8 of the way turned around. If I do another one, I'm now quarter of the way round. You're now 90 degrees off of my zenith, aren't you? Quarter of a circle. That's all we established. All we're establishing with a sextant is how far I've turned. In this case, how far round a circle I've travelled. We know how big the circle is. Therefore, if I know I've travelled quarter of the way around a circle, if the circle is 10 metres, I have travelled 2.5 metres. Boom. That's all you're doing.
Do you think I can quickly share my screen?
I'm quite happy for you to, but let's see if we.
I just want to draw something on Paint quickly for you. That's all.
Right. So there's your image. Let me just zoom it a bit. Oh, if I look at the right window.
Great. Okay.
Okay. Go on. You go.
So on the left, that's what you guys are assuming, okay?
No, it
the one
isn't.
on the left that's closer to you, okay? The horizontal line would be that red horizontal.
Well, that's okay. So just so we get where we agree and don't agree, that red line is a horizontal on both of them.
Yeah.
Okay. I'm going to
Now,
zoom
when
it in a
you-
bit more just so people can see it. Go on.
Okay.
There we go.
So when you're standing at that 90 degree, that
Here,
would be that
at this
vertical,
cross.
yeah?
Yep. Okay.
You're looking up and you're measuring an angle to the star.
Correct. Okay. So I could be using the yellow line upwards, bubble sextant, and measuring down, or I could be looking at the horizon or a tray of
No, you're
molasses.
standing using a nautical sextant at the moment.
Okay.
You're standing
Okay.
on that red
Okay.
line on the,
Okay. Yeah. I'm using, okay. In
and
this
you're
case,
looking out at the horizon.
looking
okay?
out at the horizon, and yes, we measure an angle up, make corrections, and then deduct
So you
it
measure-
from 90 to get
so you-
that one.
Great. So you're measuring the angle to the star. So you would agree
Yeah, yeah.
that adjacent and the hypotenuse is two straight lines.
It's not an adjacent and a hypotenuse. It's
Yes, it
it's,
is.
No, hold on. It's
You're
the red,
making a triangle.
Right. No, hold on a second. We're stood at that cross point, yeah?
Mm-hmm.
Yeah. So we got one ray going to the star,
Hypotenuse, yeah.
one ray going that way,
The adjacent, yeah.
and there's our vertex. That's it.
Yeah.
That's two rays
Sorry,
and a vertex.
the star has a GP on the ground, correct?
Yeah, well, for a start, it's not there. The star's GP would be somewhere
Exactly.
around there.
That's why I look to the right.
Yes, like that. So that's how the star's GP would be, yes.
Great.
But-
So would that change the angular reading?
No,
Why not?
because the angle in both of those is between the red line and, sorry, I'm a bit colourblind, whatever colour that is between, what colour is that?
It's between white and baby blue.
Okay, so we got the line from the star to the cross, line from star to the cross. What we're measuring here is the angle between the red and the line from the star to the cross. What we're measuring here is the angle between the red and the star to the cross. The fact that
No, but-
the fact that the star's GP is there or misdrawn there makes no odds. All I'm interested in is that angle. Two lines and a vertex, an
course it
angle,
makes a
as we
diff-
established
of
at the
course it
top of the
makes-
show.
Of course, it makes a difference.
Why?
You would agree because the star has to be 90 degrees, correct?
What do you mean?
The star has to be 90 degrees on Earth's surface, just like you are 90 degrees on Earth's surface.
The star is, if you're stood here, it's 90 degrees. If you're stood here, it's not.
Exactly, but I'm saying, let's say you got someone standing underneath the star at 90 degrees. They'll be
Okay,
on the
so
right.
we got someone stood there.
They're looking upwards.
They're looking
so
up,
the star is
that
right
star's,
ahead of them.
the star is right over their head. Yes. Okay.
Great. Okay, and then you got the observer standing on the top there,
There. Yes.
also at 90 degrees.
To
Okay.
what? Oh, 90 degrees to the surface of the Earth. Yes.
Yeah.
Yeah.
Okay, so they each got their own different zeniths.
Yep.
So
So
he takes-
so person A has got a zenith that points to the star. Mr. Sensible has got a zenith that points just up there somewhere.
Straight up, yeah.
Yeah.
And you take a measurement now, let's say 45 degrees to that star.
What, me? Here?
Yeah.
Okay, so
Yeah.
so I have used my sextant through all our clever means, and I established that angle there. Yes.
Okay, great. Now
I'm
I want
done.
to ask you, we're minusing the 90 degrees to get the co-altitude angle,
Okay,
correct?
so what angle were we saying? This was 45, was it? So this is 45 as well.
Yeah, but you're taking 90 degrees
Yes.
of the star's GP,
No.
and you're minusing to get the co-altitude angle of the star's GP.
What's the hold on? What's the co-altitude angle?
The co-altitude angle is the apparent angular measurement. So the
of
apparent
what?
angular measurement, the correction of the apparent angle measurement.
No.
So if
no,
you
no,
take,
no, no. Can I correct you?
If I take 45 degree measurement,
I tell you,
I have to-
let's
up
can we
to
say
minus
can we
X-
say can we say 40 so we get 40 and 50? We don't get two 45s, just to make it clear as to what we're talking about.
okay.
Okay, so it's
40,
45
you've
degrees
measured
up.
at 40.
Yeah,
You measured at 40 degrees.
Yep.
Okay. Now you have to take 90 degrees.
Yes, which
Okay.
is
And minus the 90 degrees by 40,
yep.
which gives you 50 degrees.
And where's that? That 50 is there, isn't it?
Yes, co-altitude angle.
Yes. So what?
Okay.
So just to
Listen.
So yeah, but I'll let you carry on. But just to explain. So what I've done is I have used my sextant, measured that the star is 40 degrees of elevation. Therefore, The co-altitude is 50, which is 90 minus the 40, i.e. that star is 50 degrees off of my zenith.
Great. Okay.
Okay.
So, does that star have a 90-degree angle as well?
That star has a GP somewhere.
As in
Yes.
of 90. And it
Where
has the
your
same-
matey boy is
and-
sat over there.
And it will have the same circle of equal altitude.
What does that? What do you mean it'll have the same circle of each?
It has to have the same horizontal plane. You're completing a triangle here.
No, you're not completing a triangle.
Yes, you are. You're doing triangulation. You're doing
No, you're not.
You're doing Sakatoa.
No, we're not.
doing
Okay,
Sakatoa.
okay,
Yes, you are.
okay. If you're doing Sakatoa, what's the height of the star?
You can't get the height of the star because it's
Why?
apparent. Because I've proven this with my
You just
last
said
challenge.
you just said you're solving that triangle with Sakatoa.
I can give you a citation that says you're doing Sakatoa if you want to.
Well, you're not. Okay, let me run you through what.
I can
what-
give you a citation that says you're doing Sakatoa. when
Okay,
doing
okay. Give me
selection
give me a
navigation.
give me a citation. I suspect if you come across a reference to it, it's in a different aspect of it because you don't solve any. If you solve a triangle, if you've got two angles and a side or two sides and an angle, whatever, you can solve all the lengths and all the angles. We haven't got that. And anyway, we're not interested in solving a triangle. What we're interested in,
Yes, you do.
like my example, when I was on my spinny chair, all I'm interested in is how far have I turned around. I've turned around in this case 50 degrees. Therefore, that star is 50 degrees off of my zenith. Therefore, I know the percentage or the distance around the Earth I've travelled. That gives me a distance. I didn't need to solve any triangles. Oh,
There we go.
what is that? The one that you're talking about?
Sakatoa.
Right. So what is this? Because I can't see what that says. It's quite small. Trigonometry. Yeah. The three basic trigonometry relations that we're concerned with here are sine, cosine, tangent. They're ratios of length of two sides of a particular triangle. Particular type of triangle is most useful in maths is a right triangle. One angle equal to 90. Where's it saying about this in relation to celestial navigation?
It's a whole document. This is just the one part on Sakatoa. You can go through
Yeah,
the
but-
whole
yeah, but
thing.
we know what-
I'm just going to look for the whole.
Okay, because we know what Sakatoa is. That's the whole point when flat earthers say you're solving a triangle. Well, why can't you tell me the height of the star then? Because using Sakatoa, you can calculate those sort of things.
No, remember, if you can use Sakatoa to get my height of my flask, then I can say, but you guys can't get that right. You know,
Sorry?
no one has managed to do my flask challenge yet.
I don't
It's
know
been
anything
out
about
here.
that. I don't know anything about that.
If I, are you good with trigonometry?
I can muddle my way through it. I'm not going to be able to do stuff.
If I
off-
give you
but-
the
can we? Well, the point is, this is solving triangles using sines, cosines, and tangents. You don't do that to get the co-altitude angle. The co-altitude angle tells you how many nautical miles away you are from that star's GP. That's it.
how do you
then-
get that co-altitude angle?
Well, we just done it, didn't we? We just did
Yeah.
it. Sorry, let me
Sakatoa.
just. No, hold on. Where's your image? There's your image. Okay, so I measured the altitude of the star at 40, which deduct from 90 gives me a co-altitude of 50. It's 50 degrees off my zenith, so it's 50 times 60 nautical miles away to the star's GP. I haven't solved any triangles. I've got the answer.
You do know the 90 degrees you are working with is the star's 90.
What do you mean? I'm stood here. Okay, I'm stood here. The star is 40 up.
The star is 90 degrees in reality. Otherwise, you wouldn't get
a
your
star is
complete. Otherwise, you wouldn't get your complete triangle, would you?
I'm not solving a triangle. I have taken one angle, the measured elevation, and deducted that from another angle, from 90, to find out how far off of 90 it is. So if it's 40 degrees above horizontal, therefore by definition it's 50 degrees off of vertical. Boom, that's it. I haven't solved a triangle. I've done one simple subtraction. That's all I want to know. And now I know that. I know wherever that star's GP is, could be anywhere, because I don't know them off by heart, and it depends on the time of day, but wherever it is, I am now X nautical miles away from it. I'll get my nautical almanac, look it up. Oh, there's the location of it. I'm X miles from it. That's
okay.
that's all.
Like I'm gonna ask you again. Remember, I asked you, are you good at trigonometry? So, if you measured 40 degrees to the star, okay,
Elevation.
and
Yep.
we know the internal angle, some of a triangle is 180 degrees, okay.
Yes.
So we've taken the 90, you've minused your 40, which gives you 50. So that means it would be 50 degrees of the star, correct, in the corner. On the top.
But all we're interested, Zoid, is
listen. That would be 50, correct?
Right.
So there's your co-altitude angle without without minusing.
Do you know? I
from the 90.
I think no. I think I can see where you guys are all going wrong. You're just trying. You're trying to. You've got your first. Angle, the angle of elevation of the star, as you said, 40. You know that the star is at 90 degrees to the Earth's surface somewhere, and then that gives you the remaining number of degrees. That's what you're talking about, isn't it?
I might have to draw this again because this is simple.
Yeah, it's simple. I don't see why you don't get this. I mean, look, you see your diagram, okay? If that star. Because of course, I know it's just a drawing, so the star's very close. But if that star, okay, I'm at 12 o'clock. If that star was at 9 o'clock, right over here, okay, I mean, because it's parallel light, it would appear exactly on the horizon, wouldn't it? So when I measured its elevation would be 0. Deduct that from 90, it's at 90 degrees to my perpendicular. Therefore, its GP is a quarter of the way round the world. There. At 9 o'clock.
Okay, I've given you with all the angles in.
Oh, right, you got another diagram. Okay, let's just see if I can get that one in. Nice. This one, yeah?
Mm-hmm.
Okay. Yes, that's true, but that's what I'm saying. I see where you guys are going wrong, because I'm stood here on the right. I measure the star's angle as 40 degrees. We know that somewhere on the Earth, the star is directly overhead. It's at zenith, over its GP.
Which would mean it's
90
50
degrees,
correct?
Yes, which makes 50 there. Yes. And in fact, if you were to draw a line from the star across here horizontally, that would give you a 40 up here. Of course, yeah.
So if you had to draw a line from that star now, not showing 90 degrees, would you get the same angular reading?
What do you mean if I had to draw
like we said on that other diagram that you had now previously that I drew? With on the right, that 90 degree wasn't 90 degrees anymore.
This one?
Yeah, the one on the right, the other side.
Sorry, this one. Sorry, say it again. Oh, right. So you're saying that 90...
Would that still show 50?
Right.
Would that still show 50 and 90?
Yeah, of course it wouldn't, because... but this is why you guys are going wrong. You've come from the background thinking the Earth is flat. I know that's 40 degrees. You hear of co-altitude angle deducting from 90 and taking it up there. Okay? But if that was the case... If I moved a bit further away, so I don't know how many... If I move further away, so it's no longer at 40 degrees, it's at 30 degrees, okay? The distance between the star's GP and this one won't equate to the equivalent distance between there and where I've moved to. Like...
Yeah, bring up your quick
like
picture,
that. This is why it doesn't work, because every
Sextant up again.
Hold on, look at my diagram. I know it's going the other way. So we've got the sun. Mr. S on the right has the sun at his zenith. Mr. S, the next one, it's 10 degrees off. So it's elevated at 80 degrees instead of 90. It's elevated at 70 degrees, 60 degrees. Okay, 50, 40, 30 degrees. But the distances between them aren't the same. But in actual fact, using celestial navigation with a sextant, every 10 degrees will be 600 nautical miles. This won't work.
You want me to give you what's the linear relationship why it's flat?
Please. I'm all ears.
Bring the picture of your sextant up quickly.
This one?
Yeah. Look at that index arm. Is it curved?
Well, this here?
Uh.
Where the the readings are?
Yeah. Is that curved?
Yes.
Is that an angular reading over an arc?
What we've got is we're measuring an angle. We're six.
Yeah, and is that index arm traveling over an arc?
Well, if you have a rigid object and you turn it around, the end of that object's going to trace an arc. Yes. So.
Great. So there's your linear distances. The distances come off of that linear arc.
Right.
You're closing your celestial sphere with the bottom of that arc.
You're closing your celestial sphere. No.
Mm-hmm. It's your angular reading, just like the protractor. Just like the protractor that you just put on.
Like one of these?
Mm-hmm.
What about it? Sorry. Where is it? My picture I just showed you. That one. Yeah.
Mm-hmm.
Right.
You see the bottom of that protractor, that curve, that arc? You would agree every degree measurement is the same linearly the same distance.
What's I see. So between that one and that one, it's the same.
Exactly the same.
One. Yes, but because all that is, that's a rotation, isn't it? You're rotating around the point.
On the arc, correct.
Well,
now that angular measurement is two straight lines meeting at a vertex on a arc, correct?
I'm on the flat Earth across the bottom.
No. Yes, you on the Earth, but the angular reading is an arc.
Well,
it's an opening between two straight lines.
I could draw this the other way, Zoid. Well, in fact, there's lots of Mr. Sensibles there who have taken angular elevation or used a sextant to get the angular elevation of the sun. Now, with celestial navigation, if I am 10 degrees away from zenith, I'm 600 nautical miles. If I'm 20 degrees, I'm 1,200 nautical miles, and so on. So why suddenly do these distances get bigger? I'm on a flat Earth, according to you. Okay,
I've explained it. It's that arc. You're measuring on the sextant.
Are you saying then, if each one is 600 nautical miles apart, are you saying that this guy over on the right, or this one next to him, when he took his reading, he has misread the height of the sun?
No. Straighten that curve out now of that index arm arc. What happens when you straighten it out? Will that give what you're seeing now on the bottom with that flat, not having the same linear distances anymore? If you had to straighten that curve out.
So if I distorted the image to make the curve
if you took that curve, that arc,
and bent down each side of it,
and you bent it straight,
what would happen to the Earth? The Earth would turn to a sphere or a curve. Yeah.
No.
Well, if I'm distorting that image,
you made that arc straight now. Would you still have the same linear distances?
I don't know what on earth you're talking about.
You wouldn't, because the vertex would be at a different location, correct?
The vertex is at the sun.
Yeah, but I'm saying the sextant.
With these rays, the vertex is at the sun. For me, starting from right to left, it's 90 degrees. The sun's directly ahead of me. I move a distance away. Oh, the sun appears to have dropped by 10 degrees. I move again. It appears to have dropped by another 10 degrees. We know that every mile you travel, every degree you travel is about 69 miles, each one. So every 10 degrees is 690 miles. These guys are moving, so the sun's dropping 10 degrees at a time. But suddenly, they're not moving They're not the same distance apart. The distance is greater. Now, if you've got parallel light rays on a curved surface, guess what? For every 10 degrees, it will drop this. It will be the same distance around the curve.
We've all established the sun's rays are not parallel, but
they are all but parallel.
You're literally taking a measurement, 2 straight lines from a vertex, over an arc. That sextant index arc is the degree measurement you're taking. That's why you closed what I said, the celestial sphere, and that's why you have your linear relationship on a flat Earth, because that closed arc linear reading is parallel to the horizontal of the scope.
Would you like some dressing with that word salad?
It's the mechanics behind how a sextant operates, how it works. If you didn't have it, yeah.
It's a shame. It's a shame that sailors and that would disagree with you. Then people who actually use it or know how to use it.
Okay, let's say if we took that arc on a sextant and we made it a straight angle, not an arc, would you get the same readings?
So instead of that curve, if you had like a ruler, yeah, you could do that. But then the readings.
Would you get the same readings?
Well, if you let me answer.
No, you wouldn't.
If I'm looking, let's go back to the picture.
Okay.
So this one, right. So there's your picture. Okay, you've got your index arm. Now, if that scale that's curved was a straight line, well, quite apart from the fact you wouldn't be able to swing this, but let's make the arm a lot longer so it could swing past it. Then the actual measurements, you could have those measurements on a straight line, but they would get further and further apart.
Do you understand what's happening? So it's the
yes, I understand what's happening. You have no bloody idea what you're talking about, Flatside, at all. Sorry, I don't wish to be rude, but you don't.
You just validated my argument like word for word there, mate.
Is it?
Yes. Oh, but I got another set at
Super chat,
and then we've got to close off because it is
that's fair enough. I have enjoyed this. It
was nice. I enjoyed it. It was nice and cordial. Good. Awesome Lawson Clip says, channel support and shout out to Mr. S for coming on and being cordial. Enjoy the convo. Oh, and welcome to Flat Earth, Mr. S.
Well, thank you for the appreciation. I appreciate that. I'm not quite a flat earther yet, anyway. Flatsoid might have to do a bit more to persuade me of that one. Place to finish. All right, listen, Zoid, thank you very much. It was enjoyable. It's good to talk to you again, and I hope you and your family all stay safe and well.
Awesome, you too.
All right.
I thought tomorrow night. I mean, Wednesday is going to be Mactoon, but it's next Wednesday, so. And that's on Celestial Navigation, so do stay tuned with that.
Yes, yes. So that'll be interesting. I'll have to keep a close watch on that one then. It'd be interesting to see if he has. What I'll do is I'll let him know about this stream so he can have a look, see what he reckons.
Yeah, you can do that.
Okay.
Let him prepare himself.
Yeah, and perhaps it will also save a bit of time that he doesn't have to go over certain things that we've already gone over if he agrees with me, and he can perhaps take the argument further forward.
Yeah.
Okay, cool.
Definitely.
All right, thanks again, my friend, and we'll catch up again sometime soon, yeah?
Awesome, thank you very much.
Cheers, good night, man.
Cheers, blessings.
Bye-bye. Wow, how's about that then, boys and girls? I did try it earlier on, but I didn't quite get it to work, so I think I ought to try this again.
I'm a South African. You can clearly hear I'm a South African.
Diplomatic community.
It's just been revoked.
Well, that was interesting. I did enjoy it. I do like talking to him, but there's some real confusion there. So stay safe, stay sensible. Good night.
Mr. Sensible, bring me some cheese, and get me only the best if you please. Here are some flowers, let me display them. Yea, Dr. Warlow, you have Arnold slay them. Mr. Sensible, you are a man. Every subscriber is a faithful fan. In your logic cheese. Mr. Sensible, help us out, please. Mr. Sensible, I needed proof of gravity, so I jumped off the roof. It's hard enough, let me go further. Why was I ever such a darn flat earther, Mr. Sensible? I'm such a clown. I am the laughing stock of the town. Bring your logic and your cheese, Mr. Sensible, help me out, please. Mr. Sensible, bring me a sphere, to which the waters of the oceans adhere, have explanations that let me be candid. So clear that all the fluffers understand it, Mr. Sensible. Please hear my call, the earth is not flat, so let's have a ball. So bring your logic and your cheese, Mr. Sensible.